This is the last of 3 lectures from chapter 15, all about acids and bases. And this lecture is going to focus on the types of acids and bases that aren't as commonly seen or talked about. The first will be what's called Lewis acids and bases, and the second is the fact that salts or ionic compounds can act or can render an aqueous solution acidic or basic. Lewis acid and bases are defined on the basis of electron pairs, transfer of an electron pair, rather than the typical Bronsted-Lowry definition, which is defined in terms of transfer of a proton. So let's get the definitions down first. A substance that donates an electron pair is called a Lewis base. Okay, so obviously a Lewis base, first thing it must have is a lone pair of electrons available. The electron acceptor, or the electron deficient species, is the Lewis acid. Stop for a minute and wrap your head around this and realize that these definitions are kind of the opposite of one another. So the Bronsted-Lowry acid is a proton donor, but a Lewis acid is an electron pair acceptor. Okay? So an acid is a donor in one sense and an acceptor in the different sense. That's how I remember it. So what makes a substance a Lewis acid? First of all, it's got to be electron deficient. So how can you tell by looking at something that it's electron deficient? Well, obviously, if it's a cation, it's a good Lewis acid. Okay, it's clearly electron deficient. It will clearly accept an electron pair. But there are some Lewis acids that aren't as obvious. Take boron trifluoride, for example. It doesn't have a positive charge, but of course it only has 6 valence electrons. So it does have an empty orbital that can be filled. So boron trifluoride is an example of a good Lewis acid. Lewis bases, make sure, sometimes you have to draw out the Lewis structure. For example, ammonia is a really good Lewis base. It's also a Bronsted-Lowry base. It accepts a proton, but it has a lone pair of electrons that can be used to make a bond with an electron deficient species such as boron trifluoride. So if you're not able to look at a substance and realize that it has an electron pair, you may have to draw a Lewis structure first in order to see whether or not it's a good Lewis base. Here's an example of a typical Lewis acid-base reaction. The first reaction we're going to look at could be defined as a Bronsted-Lowry acid-base reaction or a Lewis acid-base reaction. And by the way, all Bronsted-Lowry acid-base reactions can be defined as a Lewis acid-base reaction. So let's look at it from both perspectives. This substance, which is an ether, by the way, dimethyl ether, is acting as a Bronsted-Lowry base because it is snatching this proton from hydrochloric acid. And so you can see here's the base acid, and conjugate base. Okay, no surprises there. But now let's define it as a Lewis acid-base reaction. The Lewis base has an available lone pair of electrons, which can be donated to make a bond with an electron deficient species, which in this case is the proton. So now let's look at the second reaction, which can be classified only as a Lewis acid-base reaction. There is no transfer of a proton in this second one, so there's no way it can be classified as a Bronsted-Lowry acid-base reaction. However, it is a Lewis acid-base reaction. The ammonia has a lone pair of electrons that is used to make a chemical bond with an electron deficient species. species, which is boron trifluoride. Okay, so here we go. Although we don't have any outright charged species, we certainly have formally charged species. Okay, so the boron's formal charge is -1, the nitrogen's formal charge is +1. So the net charge of the whole molecule is 0. Alrighty, so the most important thing is to be able to recognize and classify a Lewis acid-base reaction. And you may also be asked to write the products of a simple Lewis acid-base reaction. Now we're on to talking about ions, which can make an aqueous solution acidic or basic. Not all ions. This concept is more difficult to understand, so this you need to be alert, and it may seem confusing in the beginning. So the first thing I want you to realize, and you need to have this in your brain throughout this chapter for a number of reasons. But if you have a water-soluble salt, what does it do when you first add it to water? You need to get in the habit of recognizing, first of all, when an ionic compound or salt is soluble, and then if it is and it's added to water, it really exists as the individual ions that are solvated by water molecules. This is important because these individual ions can then go on to react with other substances, and so it's important to see them as individuals. Some anions and cations, as I said, will make an aqueous solution basic or acidic. The first kind of sweeping generalization that I want you to remember is that if a cation changes the pH of an aqueous solution, it will always make it acidic. So think of cations and acids as being similar. Not every cation will make an aqueous solution acidic, okay? But if it does change the pH, it will always lower the pH. Likewise, anions, if they change the pH of an aqueous solution, it will always raise the pH. In other words, anions only have the capability of making an aqueous solution basic. Examples I've given you right here. This is a real obvious one, but the ammonium ion is a cation, clearly, and it makes an aqueous solution acidic. And I left off one of the products I see here by producing the hydronium ion. Now remember, when we measure the pH of an aqueous solution, pH does not measure, nor can it measure just random cations and anions. It only measures how much hydronium ion we have present. So if there's no hydronium ion, it doesn't matter what else is present. If there's no hydronium ion, we're not going to register a pH. And so because this ammonium ion produces hydronium ion, the pH drops. In other words, it gets more acidic, or it gets acidic, period. All right, so anions. I said earlier that anions, if they're going to change the pH of an aqueous solution, will always turn it basic. Let's look at how that is. Again, a pH meter is not going to measure how much fluoride anion, for example, we have. It only measures hydronium ion, which you should know by now is intimately linked to hydroxide. Remember that the concentration of hydronium times the concentration of hydroxide equals a constant called Kw. So if we're producing hydroxide in a solution, that means that the hydronium concentration has to be going down so that Kw remains constant. So here's how the fluoride ion produces hydroxide. It is actually a weak base in solution. It snatches one of the protons from water, produces hydrofluoric acid, which is not the substance that registers with a pH meter, but it also, as a side product, produces hydroxide, and that in turn changes the pH. Make sure you understand this first slide before you go on. So here comes the kind of tricky part. Which ions make a solution acidic or basic, and which ones don't, and why? So first I'm going to give you the conclusion, and then I'm going to explain why, so hopefully it makes some sense to you. An ion that comes from a strong acid or a strong base do not affect the pH. That's really, really important to remember. What do I mean when I say ions that come from a strong acid or a strong base? Well, hydrochloric acid, hopefully you've memorized your 6 or 7 strong acids. If not, you need to do so now. Hydrochloric acid is one of the strong acids. What is its conjugate base? It is the chloride ion. Therefore, the chloride ion never changes the pH of an aqueous solution by itself. So if you were to add sodium chloride to water, remember it's soluble, and so how did I say soluble salts will exist as the solvated ions? This ion, the chloride ion, will not change pH. Therefore, when you add sodium chloride to water, it has a pH of 7. It is not going to make it acidic or basic. Similarly, sodium hydroxide is a strong base. Again, you need to have those 6 or 7 strong bases memorized. When sodium hydroxide dissociates in water, you get the sodium ion and the hydroxide ion. This sodium ion, therefore, is an ion from a strong base, and that means the sodium ion does not change the pH in an aqueous solution. And so that fits with we know that if we add sodium chloride to water, that water is going to maintain a pH of 7. Neither the cation nor the anion in sodium chloride, because they both come from a strong acid or a strong base, will not change the pH of water. Let's look at cations and anions that do change the pH in water. And those are all ions that come from a weak acid or a weak base. Let's look at an example. Potassium nitrite. Okay, that is a soluble salt, and so when we put it in water, we want to draw out what happens. We get the solvated potassium ion and the solvated nitrite anion. Since the nitrite comes from a weak acid, it can change the pH of water. Remember what I said, anions will always make the pH of an aqueous solution basic. Let's see how it does that. Here's the nitrite ion. When we put it in water, it acts as any base. It snatches a proton off water to reform nitrous acid and the hydroxide ion. It is the hydroxide ion or the hydronium ion, as I've said before, which can change the pH. So the pH of this solution is going to be basic because we've produced hydroxide ion. Let's look at the cation. Potassium nitrite also has a potassium ion. That potassium ion comes from a strong base, KOH. Okay? What does that tell us? If it's from a strong acid or strong base, there's no pH change. Okay? So this problem is made more simple. We can ignore the effect of potassium changing the pH and focus on the anion that comes from a weak acid, and we know that we have a basic solution. My guess is you're going to have to go through a few of these before they begin to make sense for you. I want to take just a minute and show you why potassium ion doesn't change the pH. Let's imagine that the potassium ion reacted with water. What would you get? Well, anytime a cation reacts with water, you would get the hydroxide and then what's left over, H+. Okay? And so get familiar with what you do if you have a cation reacting with water. So if this reaction did occur, the cation would be capable of producing an acidic solution. But the question is, why doesn't it occur? Well, let's look at what has formed. We've formed potassium hydroxide, which we know is one of the strong bases. What's the definition of a strong base? The definition of a strong acid or base is that they dissociate completely. In other words, KOH does not exist in water as an intact molecule. So even if the potassium ion makes a few KOH molecules, they are immediately going to dissociate back into the individual solvated ions. And so really no significant amount of the hydronium ion can remain formed because it's just not stable. And that's true of all cations from strong bases. So let me go through the steps. You may want to jot these down, and I want you to try some on your own. If you're given a salt or an ionic compound, the first thing you need to do is determine if it's soluble. If it's soluble, then the first thing is to dissociate the salt into the cation and the anion. Then you ask yourself whether each of the ions, the cation and the anion, come from a strong or a weak acid and a base. All right? So cations, in order to answer that, the cations, just add hydroxide to it to see whether or not it comes from a strong acid or a base. Okay, magnesium. So let's imagine magnesium hydroxide. Is that a strong base or a weak base? It's one of the weak bases. Okay, so this is now, if you haven't memorized these, you need to now. And so let's imagine we were looking at the anion fluoride. What you do with an anion is you add a hydrogen ion to it, okay? And then you ask yourself, is that strong or weak? Hydrofluoric acid is weak, therefore it can change the pH, okay? So magnesium's out. It's not going to have an effect on the pH, but the anion will. How do anions change the pH? Remember, they make it basic, okay? So if we were to add magnesium fluoride, it's a soluble salt, to water, okay, the magnesium would not contribute to changing the pH, but the fluoride would make it basic. So that is actually the truth. If you get magnesium fluoride, dissolve it in water, you will find that you have a solution of about pH 8 something. How do I quantify information about pH and concentrations? Just like you do any weak acid or base. So fluoride is a weak base. You would simply write the equilibrium expression as you always do. This would be an example of a Kb. And set up an ice table with the given information, and just like you always do. All right, no change there. Let's go ahead and do an example now. Here's a salt or an ionic compound. In case you've gotten fuzzy on how to identify that, an ionic compound has a metal and a nonmetal. This happens to be a polyatomic ion. And it is soluble. So to remind you of some of the solubility rules, any ionic compound that has a metal from group 1A is automatically soluble. So go through that list of steps I told you to solve this. And since it's soluble, the first thing you want to do is break it into its cation and anion. And then decide whether each of these comes from a strong or weak acid or base. Remember what I said to do with the cations? I said make them into a hydroxide, and ask yourself, is that strong or weak? Sodium hydroxide is a strong base, which means the sodium ion will not change the pH of an aqueous solution. To anions, you want to add a proton, and so what do we have? Is that a strong or a weak acid? That is a weak acid, and you don't have to know that specifically, but you should know it's not one of the 6 or 7 strong ones, therefore it's weak. So that means this anion can change the pH of the solution. How is it going to change it? it's going, as all anions that are from a weak acid, it's going to make the aqueous solution basic. Let's go ahead and figure out how basic it makes it. Here's the information you need to set up your ice table. Since the substance we're concerned about is the anion from a weak acid, that is the equilibrium you need to set up. So before you can make an ice table, you have to find the correct chemical reaction and equilibrium that's occurring. And so, of course, it's acting as a base. So we're going to reform the acid, and what's going to be left over after it snatches a proton from the water is hydroxide. Set up your Kb expression. Because it's acting as a base, right? And probably if I were working this problem, I would have done this, and then I would have gotten ready to fill in the value of Kb. So I probably would have gone back to the question and said, whoops, they didn't give us Kb, they gave us Ka. So the first thing you need to do is convert the Ka value that was given to you in this reaction into Kb. So you need to remember that the relationship between the two, Ka times Kb equals Kw, which at 25 degrees Celsius is equal to 1 times 10 to the minus 14. So that means it's pretty easy to find one from the other. Kb is Kw divided by Ka. So there's the Kb value you need. And now you just set up an ice table. And I just happen to notice that I left out a carbon here. It doesn't change the reaction at all. But acetic acid has 2 carbons. All right, so I have it right here. Good. Okay, so here's the equilibrium we're dealing with. Starting with it's called the acetate ion. It snatches a proton from water, produces hydroxide, and go ahead and set up your ice table. Let's look at the Kb value so we can make a decision whether or not this X is negligible. Kb is 5.6 times 10 to the minus 10. That is a very small Kb, so we are absolutely safe in neglecting the X. And now you can plug these equilibrium values into the Kb expression. When you do so, you get that X is equal to 5.75 times 10 to the minus 5 molar. Don't stop there. A lot of people stop there. It's so much work getting to X. They're like, I'm done. No. Make sure you go back and see what is X. Look back at your ice table. What have you just found? You have found the concentration of hydroxide. The question asks for pH, so you're not quite done. So how do you get POH? I would do that first. POH equals, minus log of that concentration, 5.75 times 10 to the minus 5. POH is 4.24, and then of course you find pH by subtracting the POH from 14. So the final answer is a pH of 9.76. Does that make sense? Yeah. We're working with the acetate ion, which as all anions, if they change the pH of a solution, it's going to make it basic. 9.76 is basic, so it makes sense. Normally I'm not crazy about huge concept maps, but I thought this one was really good in the end of the chapter. So what have we learned? We're done with chapter 15 now. What have we learned about acids and bases? Well, some of the key terms that you need to know, amphoteric, remember, means it can act as something that can act as an acid or a base, and water is the most common amphoteric substance. We learned how to calculate pH and POH, so this should be your prompt that you need to make a list of formulas that you need to have memorized that involve pH and POH. We learned how to deal with strong acids and bases, and that it's pretty easy to find the pH and POH of strong acids and bases. You simply use the minus log of the concentration directly. No ice tables, okay? And then we learn that dealing with weak acids or bases is a little more complicated. If we're dealing with a weak acid or base, we have to consider the equilibrium constant. Strong acids and bases have no equilibrium. They convert completely to their conjugate acid or base. So there's no Kb, no ice table. If it's weak, Ka, Kb, ice tables. And after you do all that, then you use the minus log formula and get pH. We learned there are a number of different definitions for acids that you need to be familiar with. And as kind of a side note, we learned that water itself can auto-ionize. So that was 2 molecules of water on their own in neutral water will form a little bit of hydroxide and hydronium ion. And because of that, the product of hydronium ion and hydroxide ion is always the same. And that product is equal to Kw. So that's it for chapter 15.